I'm Nicola Rennie, a lecturer in health data science at Lancaster University. Welcome to the 2024-2025 William Guy Lecture aimed at secondary school students. I'm going to be talking about how we use statistics to help make decisions in medicine and healthcare. But before we get into that, I want to take a moment to tell you a little bit about myself and how I ended up here talking to you. So when I was at school, I didn't really know what sort of job I wanted to do. I quite liked maths and science subjects, so I decided to go to university and I studied maths. And I picked maths because it seemed like it left quite a lot of different career options open. Lots of jobs use numbers. And it was at university that I first learned about statistics. So statistics is a part of maths that involves collecting, analysing, and interpreting data. It's about taking lots of information, like numbers or facts, and using it to understand what's happening and to make decisions. So to me, this idea of statistics seemed quite useful and quite interesting. So I decided to learn a bit more about it, and I continued studying statistics. And one of the things I really like about statistics is that you can work in lots of different areas depending on what you're interested in. So since I started working with statistics, I've worked on projects that include modeling how many people book tickets for different train journeys, understanding how much fishing is happening in our oceans, investigating changes in life expectancy and retirement age, and also exploring how flu spreads in schools. But what I'm going to talk to you about today is using statistics in medicine. There are lots of examples of using statistics in medicine, whether that's to investigate where an infectious disease outbreak started, to explore the risk factors for different diseases, or to study whether different medical treatments work. And when we do a study of new medical treatments and look at their effects on human health, we typically call this a clinical trial. One of my favourite examples of a clinical trial goes all the way back to 1747. And at that time, a disease called scurvy was a huge problem for sailors on ships. So scurvy is caused by not having enough vitamin C. Although in 1747, we didn't really know that. But James Lind, a Scottish doctor in the Royal Navy, selected 12 patients with scurvy on a ship and gave them each one of 6 possible treatments. Some of the treatments included drinking vinegar, eating garlic paste, drinking seawater, or eating citrus fruits like lemons and oranges. The sailors whose daily diet included the citrus fruits recovered, but the others still had symptoms at the end of their treatment. And this helped to show that citrus fruits could cure scurvy. It's one of the earliest examples of a clinical trial. Coming back to the modern day, now clinical trials are used to test the safety and effectiveness of all kinds of medical treatments. So let's think about a more modern problem. I want you to think about the last time you had a headache or an earache, or maybe you just weren't feeling very well. So maybe you told your parents or a teacher or another responsible grown-up that you weren't feeling very well. And maybe they gave you some medicine or they took you to a doctor or a nurse who gave you some medicine. How did they know that that medicine would work? How did they know how much of that medicine to give you? And how did they know it was safe to give you? Some of you might have seen or heard discussions about some of these questions a few years ago when COVID vaccines were first introduced. But it's not just vaccines we're talking about. We need to understand these questions for all medicines and all treatments. And maybe the obvious answer to these questions is that the medication has been tested. But that's a very simple answer to a lot of difficult questions. How can we be quite certain that a medicine is working? How many people should a medicine be tested on? And how do we decide which people it should be tested on? That's where statistics comes in. So let's say someone has developed a new treatment for high blood pressure. So blood pressure is the force of your blood pushing against the walls of the blood vessels in your body as your heart pumps the blood around your body. And you can measure your blood pressure using a blood pressure monitor. It's usually a cuff that wraps around your arm. And you can measure it at home, or you can have a nurse or a doctor measure your blood pressure for you. So these monitors usually give us two numbers back out, a maximum and a minimum blood pressure. And if these numbers are high, so if they're above some threshold, then the person would have high blood pressure. And high blood pressure can increase the risk of other more serious health conditions. So it's important that it gets treated. So how do we test if this new high blood pressure treatment works? So let's start with the first question. What do we mean by the treatment works? We need to start by deciding what we're going to measure. So we could measure someone's blood pressure after they have taken the new treatment. But that doesn't really tell us much about the treatment. We don't know if their blood pressure has actually changed if we only have one number. Instead, we need to measure the change in blood pressure before and after treatment. So we measure someone's blood pressure, then give them the new treatment, maybe for a few weeks, and then we measure their blood pressure again. And we can look at the change in the two blood pressure readings. Right? To keep it simple here, we'll just look at one of the two blood pressure values, the maximum. We usually call this maximum blood pressure the systolic blood pressure. So if the blood pressure has decreased, if it's come down, does that mean that our new treatment is working? Well, maybe. Blood pressure changes a lot during the day. For example, it's usually higher when you're hungry, and then it reduces after you've had lunch. So maybe the blood pressure reading is only lower because the person just had a sandwich rather than because of the new treatment. We could ask a patient to do the blood pressure measurements at the same time of day, but we can't control for every factor in a person's life. So one way we deal with this is by testing the treatment on lots of different people. So then, how many people do we test? 5? 500? 5,000? 5 million? 5 probably isn't enough. We probably need more than 5 if we want to be more certain that any change is because of our new treatment. 5 million people is almost certainly enough, is actually probably more than enough. And including 5 million people in our study is very expensive and very inconvenient for 5 million patients. So we know it's somewhere between 5 and 5 million. How do we decide on a more specific number? So first, we need to decide how sure we want to be. Imagine you want to be very confident that your results are very close to the truth. This is like saying, I want to be very sure that the results from my tests are similar to what would happen if everyone took the medicine. The more sure we want to be, the more people we need. We also need to estimate how much people's reactions might vary. So, for example, if you think almost everybody will have a similar reduction in blood pressure, there isn't much variety. But if you think some people's blood pressure might drop a lot, and some people's only a little bit, there's a lot of variety. And the more variety there is, the more people we need. We also need to think about how big a change in blood pressure we expect. If we think the change in blood pressure will be very big, then it will be easier to spot. If we think the change in blood pressure will be quite small, it's harder to check if the change is real or if it's just variability. The smaller the change we're trying to find, the more people we need. But once we know these pieces of information, statistics helps us to calculate the minimum number of people that should be included in any clinical trial. So we know how to decide how many people to include in our study. Often we don't just want to know if a treatment works. We want to know if it works better than something else. So we need something to compare our new treatment to. And maybe all of these people would have decreased their blood pressure anyway. Maybe the test was done in summer and they all started doing more exercise, for example. There are a few different options for what we compare our treatment to. We can compare it to no treatment. So does this new treatment improve blood pressure more than not taking any medication? In medicine, that's not always a good comparison, because that means that some people would receive no treatment for their high blood pressure, and that's not good. So we often compare it to the new treatment, to the current treatment, for high blood pressure. If we're comparing a new treatment to an existing treatment, how do we decide who gets which one? Often, if we have two treatments to compare, we might want half of the people to get the new treatment and half to get the current treatment. To make sure that the study is as fair as possible, we want to randomly decide which of the two treatments each person gets. A little bit like flipping a coin. You get heads, you get the new treatment, tails are in treatment. We do this to make sure, or to reduce the chances, that something other than the treatment is responsible for any changes we see. For example, imagine the first 10 people were given the current treatment and the next 10 people were given the new treatment. But what if more people who are sick go to the doctor first and then get the current treatment? It might look like the new treatment doesn't work as well, but it's actually only because they weren't as ill to start with. Sometimes this coin flipping approach means we don't get exactly half and half for each treatment. Try flipping a coin 10 times. Do you get exactly 5 heads? Probably not. This isn't as much of a problem when we have lots of people in a study. But if we only have a small number of people in the trial, we can use more complicated statistical methods to make sure we get equal group sizes. So we've decided how many people to include in the study, and we've decided which treatment each of them will have. How do we determine if our new treatment is better than the current treatment? For each person, we have information about their change in blood pressure before and after treatment, and we know which treatment they received. One of the things we should do is look at the data and make some plots. A density plot can be really useful for this type of data. A density plot is a type of graph that shows where data points are bunched up and where they are spread out. Here's an easy way to understand it. Imagine a pile of sand that you pour onto a table, and the sand forms a hill. So the highest part of the hill shows where most of the sand is, and the sides show where there's less sand. So now, instead of sand, imagine each grain of sand is a piece of data. So here, each grain of sand is the change in the person's blood pressure reading. Where the hill is highest, that's where most of the data points are. So in this example, lots of people had a change in blood pressure of about 3. A few people had a bigger change, and a small number of people had an increase. Now, we can compare the density plots for each type of treatment. Okay? So here, the blue plot shows the change in blood pressure for people who had the current treatment, and the yellow plot shows the people who had our new treatment. You can see that with the new treatment, we have a higher drop in blood pressure compared to the current treatment, so that sounds good. And here, there's a small overlap between the two, but it generally looks like the two treatments are quite different to each other. Let's look at another example. Here, it gets a little bit harder to say whether the new treatments are actually different from each other, when there's more of an overlap. Here, the new treatment is still a little bit higher, but there's a lot of overlap between these two plots. We can use statistical tests to tell us if it's likely that the difference between the two treatments is actually real. Of course, it's not just about whether treatments are different according to statistics. We need to think about whether they're different enough to make a difference in medical treatment. A new treatment might be much better at reducing blood pressure according to statistics, but if it only reduces blood pressure by, let's say 0.5, right, when in reality we were looking for a number closer to 10, then it might not be enough of a difference to decide to invest lots of money in developing the new treatment. Statistics is a very important part of medical research, but it works best when statistics experts work closely with other people involved in medicine, such as doctors, nurses, biomedical scientists, or technicians. I hope you've been able to see from this talk that Statistics can lead to a wide variety of jobs, and that having a career within healthcare and medicine doesn't always mean being a doctor or a nurse. So before I finish, I just want to say thank you very much for listening to the talk. And if there's anything you do want to discuss in it, please do get in touch.